Okay, so now we'll take a look at creating confidence intervals. When we spoke about the central limit theorem and sampling distributions, we said that if we collected a bunch of samples of the same size being n, and those samples were either from a normally distributed population, or the sample size n was large enough, and we said large enough was roughly greater than 30. Then, when we collected all those sample means, if we collected a whole bunch of samples of size, let's say 100, and we calculated all the sample means, the distribution of those sample means would be roughly normal, and the mean for those sample means would be the population mean, and the standard deviation for those sample means would be the population standard deviation divided by the square root of n. So we came up with this formula for calculating the z-score for a sampling distribution. Well, in most real life situations, sigma, the population standard deviation, is not known. And to adjust for that, instead of using the z distribution, which is centered at 0 with a standard deviation of 1, we are going to use the t distribution, which the t distribution is very similar to the z distribution. It's centered at 0, but it allows for a little bit more variability. You see the tails in the t distribution are thicker. The tails are thicker. As n tends toward infinity, as the sample size gets larger and larger and larger, or approaches actually not infinity, but the population size, as n approaches the population size, t actually approaches z. Um, but both of these distributions are centered at 0, and we are going to use this transformation to t instead of the transformation to z whenever um, the population standard deviation is not known. All right, so let's talk about the margin of error, or sample error. Okay, sample error is the difference between the point estimate and the parameter. So for instance, if we're using x bar to estimate mu, if you're using the sample standard deviation to estimate the population standard deviation, then whenever you take a sample of a certain size, um, there is an underlying population parameter mu that you're trying to estimate. You never really know what mu is, but the difference between your sample mean and your population mean, that's going to be what we call the sample error. Okay, if you notice, the numerator of the t-score formula is x bar minus mu, which we just defined as the sample error. The sample error, once again, is just the distance from the mean to the sample, from the population mean to the sample mean. Okay, so let's see. That means that we can replace x bar minus mu in this formula with e, the sample error, the margin of error. And if we wanted to solve for e and get a formula for e, we could just multiply both sides of this equation by s over the square root of n, and that would give me e equals to t times s over the square root of n. So this is how I'm going to calculate my margin of error, okay? And what we're going to do is we're going to look at creating confidence intervals based on x bar, okay? Now, in the case where x bar is larger than the mean, what we're going to do is we're going to say we want to make sure that that margin of error is large enough so that if I start at x bar and extend it below x bar, it'll get to the mean. It'll get to the mean, okay? The population mean. And I want to make sure that if that x bar, that sample mean, is too small, if I take my margin of error and I add it to x bar, I will be able to capture that population mean. So basically, if I overestimate, if X bar is an overestimation, I want to make sure my margin of error is large enough so that when I subtract that margin of error from X bar, I get a number here that for E that will take me beyond mu so that I know that I have captured mu. And I also want to make sure that if it's too small, I add the right number so that I capture mu. Okay? So that's what I'm going to do. I'm going to take my X bar. I'm going to take my X bar. I'm going to calculate what the margin of error has to be in order for me to have a large enough window to say that I have captured mu. Okay? Now, once you have created that interval, there's going to be a certain confidence that you're going to have that you have captured mu, okay? And that confidence level is actually going to be panned out, is going to be shown out um, around mu, okay? So we're saying that we know that mu is within E of whatever the sample value is here, X bar. So basically, if we take mu and we add E to it, I know that that sample will be captured. And vice versa. If I take mu and I subtract it, I know that whatever that X bar is will be captured. So that's the confidence level, okay? I want to create a 95% confidence level for human body temperatures in this example. So I'm saying human body temperatures are normally distributed, so they have this bell shape. A sample of 49 human body temperatures has a mean of 98.2 and a standard deviation of 0.42 degrees Fahrenheit. I need to create a 95% confidence interval for the means here. So what I'm going to do is I'm going to try to find t values such that 95% is in the middle here, and the rest of it, because underneath this thing you have 100%, right? The rest of it I want to be in the two tails here, in the two tails. Well, since the confidence level is 0.95, we can calculate what's called alpha. Alpha is 1 minus the confidence level. That's what we're calling alpha, the significance level. And alpha in this case is 0.05. Okay? The significance level 0.05. What I want to do is I want to take half of alpha and put it up here, and take half of alpha and put it back here. So half of alpha, half of 0.05 is 0.025, and the other half I'm going to put back here, 0.025, okay? So once you know your confidence level, for me it's 95%, you put 95% in the middle, and then you calculate what half of alpha is. Calculate alpha first, and then put half of it in the upper tail, half of it in the lower tail. You're going to try to find these two t-scores, these two values for t. And then we're going to use this formula right here to change these two values for t into values for x bar, okay? Into values for x bar. And those values are going to be bounds for mu. So I'm going to have a lower bound for mu and an upper bound for mu. The upper bound is going to be the 97th percentile, the 97th percentile of sampling means. So only 2.5 or 97.5, sorry, it's going to be the 97.5 percentile. 0.95 plus 0.025 is going to be the 97.5 percentile of sample means. So only 2.5% of sample means would exceed it. And the number that I'm going to get below when I subtract is going to be the 2.5 percentile of sample means. So only 2.5% of sample means would be below, 97.5 would exceed it. So basically, I'm making sure that only 5% would be the outside here. So I'm 95% confident that my interval is going to capture the true mean. Okay, so let's see. We need to find this t-score. So we go to the t-table, and on the t-table, remember that what we just said is we wanted .025 in the upper tail. This table only gives me the upper tail. So that's what I look for. I look for an area. I look for an area in the upper tail. I look for an area in the upper tail of .025. So I want the area of .025. I want that area. But I also want degrees of freedom. The degrees of freedom. For the t distribution, degrees of freedom are equal to n minus 1. For my particular problem, that means that the degrees of freedom are 49, because I had 49 body temperatures, minus 1, so my degrees of freedom are 48. All right? Once you find your degrees of freedom, 48, you're just going to look for where the column that has the area, the correct area that you're looking for, and the row that has the degrees of freedom, you're just going to look for the intersection of those two, the intersection of that row and that column. So I have the number 2.011, 2.011. So since this is symmetric, I know this is 2.011 above, oops, saying something and writing something different. I know it's 2.011 above here, and it's also negative 2.011 below here. Okay? So I'm going to use this distance to create my margin of error now. 2.011 is t. So 2.011 is t. So back to this, let's see. I just found out that the t score that I need is 2.011. 2.011. So I'm going to plug that in to the formula to calculate the margin of error. So the margin of error E is going to be equal to, we have 2.011 multiplied by S, the sample standard deviation, 0.42, all divided by the square root of n, which is the square root of 49. All right, so calculating the margin of error then. All right, and the margin of error turns out to be 0.12 approximately. So my margin of error is approximately, when I round it to two decimal places, 0.12. Okay, here's what that means. That means that if my sample mean, if my sample mean of 98.0 is too high, my sample mean of 98.20, let's say it's too high, right? Then what I need to do is I need to make my margin of error 0.12. So this margin of error, E, would equal 0.12, and I would subtract that so that I can be sure that I capture mu with 0.025 in this upper tail, 0.025 in this upper tail. So if I want to be sure to capture mu, I have to take 98.20 and subtract 0.12 from it. So let's see, 98.20 minus 0.12 gives me a lower bound of 98.08. So the lower bound in my confidence interval is 98.08. Okay, now let's say my estimate of 98.2 was too low. Let's say it was down here, 98.20. Let's say it was too low. Well, I want to make sure that the margin of error here, E, I want to make sure that E is equal to 0.12 so that I can capture mu once again with only 0.025 in this lower tail. So that means I'm going to take the 98.2 and I'm going to add to it in this case. Instead of subtracting it, I'm going to add to it the 0.12, and in that case I get 98.32. 98.32. So that means that my upper bound then is 98.32. And if I create this confidence interval, if I use this for my confidence interval, right, I can be sure that if I overestimated the population mean, this will capture the population mean, and I can be sure if I underestimated the confidence in or the population mean, this number will capture um, the population mean. So basically, I'm 95% confident that the true population mean is between these two numbers, or the procedure that I just used would capture the true population mean 95% of the time.